Hi everyone, I'm Ignacio Clavera, and I'm going to talk about Kalman filters today. So before talking about Kalman filters and all the machinery, we'll first need to do an overview of multivariate Gaussian variables, because this is like all the mathematical background that we will need in order to properly understand Kalman filters. When we explain Kalman filters, since they're just valid for the linear setup, we will explain two extensions of it for the non-linear case. One will be the extended Kalman filter, and the other one will be the unscented Kalman filter, also known as sigma point filter. So let's first talk about the multivariate Gaussians. So a multivariate Gaussian is defined by two parameters. One is a vector mu, and the other one is a matrix sigma. And this equation on the top is a definition of the PDF of multivariate Gaussian. And it's essentially defined by this term as the exponential. So essentially multivariate Gaussian is defined by being the quadratic, like the exponential of a quadratic. And we see that the parameter mu acts as a location parameter, just centers the PDF, and the sigma parameter acts as a scale parameter. This sigma, this matrix, cannot be whatever matrix. It has to satisfy three conditions. The first one is that it needs to be symmetrical. The second one is that it needs to be positive definite. And the third one is that the inverse needs to exist, because we will need to take the inverse here. So we don't want this to be ill-defined. The other term of the PDF, these scalar terms here that depends on pi, the dimension, and the determinant of the matrix sigma, simply acts as a normalization constant. So thanks to this term over here, we have the integral over all possible x's. It's equals to 1. So this relationship will be pretty important in the lecture. So this means that the integral of these exponential terms, it's equal to the term in the denominator, and we will use this little further on. First, some quick notation. Given a matrix A, whenever we write down the A between bars, it denotes that it's the determinant of this matrix. And then when we see A to the power of -1, since like here and here, it denotes the inverse of this matrix. So essentially the inverse satisfies that the A to the power of -1 times A is equal to identity, and A times A to the power of -1, it's equal to the identity as well. And for all these equations and formulas, it's usually easier if you think of it in the one-dimensional case. So essentially, instead of these matrix being n by n, just think as being 1 by 1, which essentially means that this is a scalar. Which is the case of the univariate Gaussian variable. We have in the 1 by 1 case, we have that sigma is equal to the square of the lowercase sigma, and then we have this x minus mu transpose times x minus mu is simply x minus mu squared. So essentially, we essentially obtain the same PDF as in the univariate case. Now we will explain what all of these mu and sigma parameters mean. As probably all of you will have imagine of the mu i, that is the ith component of the parameter mu, refers to the expectation of the random variable x, the ith component of the random variable x. So essentially, if you do the expectation of xi, you end up obtaining the mu I. And then here we have the vector notation, where the integral of this vector x with respect to the PDF essentially means that taking the integral, the scalar integral, so the integral that probably all of you are used to do for each of the dimensions. And this extends the same to the matrix case. So if we compute, so the matrix sigma, essentially the component ij, it's the covariance, so it's the ij components of the covariance matrix. And we can say, because this essentially is the definition of the covariance, so xi minus mu I times xj minus mu j, if you take the expectation of this multiplication, essentially this is the covariance between these two random variables. And if we do the integral of that, we end up obtaining that this is the ij component of the covariance matrix and the sigma matrix. And in the vector notation, or matrix notation in this case, what this integral means is just doing the integral for each of the components of the matrix. Okay, now we'll see some examples of how these parameters affect the underlying PDF. So here we have a Gaussian distribution that is centered around 1, 0. So we see that in the first axis, the mu is centered in the value of 1, and then the second axis is centered at the value of 0. So we have that this shape around the value 1, 0, and then we have a diagonal covariance. That's essentially the identity matrix. So if we change the parameter mu, essentially what we have is we just move the entire function to be centered around another point. So right now this is centered around the point minus 0.5 and 0. And we can just keep shifting this around by just changing the parameter mu. That's why I say before that mu acts as a location parameter. So because it's just preserving the shape, but just moving the entire distribution around. So now we play what happens if we change the covariance matrix. So here in this function, we have just kept the mu the same, but we have just scaled the covariance matrix. In this case, we have shrinked it. So now instead of having values, the diagonal terms to be 1, 1, it's 0.6, 0.6. And what this results is that this new random variable has less variance, so all the mass is centered around mu. And what this means is like it has the PDF has higher value on mu and then nearby points compared with the identity covariance. And instead, what we do is shrinking the covariance matrix. We just make it larger. What we end up having is that the points around the mean have actually have a lower value than the previous ones, but the points that are further away from the mean have a slightly higher value. And the reason why is that when it has these different heights is because it has to integrate to 1. So if you make the points farther apart to have larger mass, that will contribute to the points that are around the mean to have lower mass. So now we'll consider the cases where the covariance is not diagonal, but it has terms that are like off diagonal. Essentially, we have a covariance matrix that is 1.5, and the second row is 0.51. What this means is that there is a positive correlation between the first axis and the second axis, and we can see it in the shape of this distribution. So what this means is like if we increase the value of the variable x, the probability of y having a higher value also increases. And that's why it has this sort of elliptical shape that is aligned to the x equals y. So we have this x equals y that has that is where this ellipsoid is one of the axes of this ellipsoid is aligned. And then we can correlate them even more by just increasing the value of these off-diagonal terms. And in the limit of this being close to 1, because if it's 1, then you won't have the covariance won't be invertible. But in the limit of this being close to 1, what we'll have is almost just one line, and a very thin type shape. We can see this what I was referring about, like the ellipsoids and the and the different shapes. So in the first one, we see that this is a perfect circle where there is no misalignment of the axis. However, in this case, since there is correlation between x and y, we see that there is one of the axes of the ellipsoid is this y equals x term, this like diagonal line. And here we see that this distinction, or this axis, is even more sharp. Here we have other cases in these 2D contours, and we can also have correlations that are negative. So here we have, if the value of the y-axis increases, actually it's more likely for the x to be negative, and we have even stronger correlations when those are negative. And also we can have cases where the diagonal terms doesn't have to be 1; they can just be scaled up at any constant. The only conditions that, as I said before, the covariance matrix needs to satisfy is that it's invertical, it's symmetrical, and it's also positive definite, so its eigenvalues are larger than 0. So given a multivariate Gaussian distribution that is high dimensional, or has more than 2 dimensions, we want to be able to write it down instead of in terms of its components. So you can imagine a random vector, and just split this random vector into two sets. One is x and y, so the concatenation of those leads to the original vector. And we want to be able to write down the entire vector in terms of the expectation and covariance of x and y. And why is this useful? This is useful because we will have to operate these higher dimensional vectors. We'll essentially have to do marginalization and condition with respect to some entries of the vector. So we want to be able to manipulate in terms of the partitions. So this is pretty straightforward. We can just write down the mu and the sigma instead of like the mu x and mu y. They're respectively the mean of the vectors x and y. And then the covariance matrix can be written down as a block partition matrix, with which each of the entries are the covariance of x, and then the covariance between x and y, and the variance and the covariance of y. So here we have all the relationships. And furthermore, we can have a dual view of the Gaussian variable, where instead of writing into the covariance, we write it in terms of the precision matrix. That is the gamma function that is the inverse of the covariance. And the reason why it's useful is because doing algebraic manipulations with the inverse, it's very tedious. So it's much more convenient if you can write down the PDF without having to deal with inverses. So now the PDF just depends on the precision matrix, and it doesn't depend on the inverse of anything. So using the qualities for the inversion of block partition matrices, it's pretty straightforward to verify this set of relationships. And I don't know if someone will notice, but this is the Schur complement of the precision matrix. So this is a relationship that occurs very often in algebra. And then since the precision matrix is the inverse of the covariance, we have that the covariance is the inverse of the precision matrix. So just swapping the roles of sigma and gamma, we can get the other relationships that tell you how to obtain the precision matrix with the covariances terms. So the first operation that we will see, it's a marginalization. So essentially, given the joint distribution of x and y, where this defines a multivariate Gaussian random variable, we want to find out the distribution of just x. So we have no idea of like what distribution whatsoever will be. So we will do all these algebraic operations with the precision matrix because, as I said before, it's more convenient and easier to manipulate instead of having the inverse of the covariance here. So in order to find out what's the marginal of x, what we need to do is just integrate out the random vector y from the PDF. And this math looks pretty daunting, but we will work through it step by step, and we'll see that it's like pretty straightforward to obtain the marginal of x. So the first line over here is just expanding out, and the PDF, and we essentially discover that we have this term over here that just depends on x, and then this term that just depends on y, and then this other term that depends on x and y. So this term that depends on x, it won't be involved at all with the integral, because it's just the integral with respect y. And then the other terms, this just depends on y, and this depends on x and y. It very much resembles like a quadratic, and it's very hard to integrate the exponential of a quadratic. But we know for almost the first slide, so if we go back to it, that if we have a quadratic of this form, we know that the integral, so just moving this constant to the to the other side of the equality, we know that the integral of this exponential over here, it's equals to these terms that involve the 2 pi, the dimension of the Gaussian variable, and the determinant of the covariance matrix. So if we are able to write down the terms of the exponential, so it's like something that has this form, then we'll know what's the analytic value of the integral. So, and that's what we will try to do in this case. So let's say the first term doesn't depend on y, so we'll just completely ignore it. And then the second term, we already have some sort of a quadratic term, right? But this is not quite what we want, because there's other ways we don't know what to do with this other term over here. So these two terms will just stay as they are. And essentially what we will do now is just having the completion of squares trick, but in higher dimensional. So we'll try to do the typical term of like a plus b squared equals to a square plus 2 times ab plus b squared. Right, so we'll try to do this in the higher dimensional term. So here we can consider it like this first term is the a squared, and then we have to be able to write it in like 2ab squared, like 2ab. So we already have the 2 here, which is nice. And then we can consider that this is like the this a squared. So now what we can do simply is just add this term over here that is doing nothing, because like gamma yy times gamma yy inverse is just equals to 1. So we have added this term that doesn't modify at all the equation, but they give us the a component, right? Because now we have y minus mu y times gamma yy. That is sort of like the square root of this term over here. And then we just need to deal now with the b term. And now we see that the b term is this sort of like gamma yy inverse times gamma yx times x minus mu x. So what we do now is just add all this b term square and subtract it again. So we haven't modified at all this equation. The only thing that we have done is just adding this 1 over here in form of like the gamma times its inverse, and then adding and subtracting this b squared term. So this part over here actually also just depends on x, so it won't be involved at all with the integral. So now what we do is like just put in front all the terms that just depend on x and won't be at all affected by the integral. And then now we have the other terms that has the y involved. But this term now is like, as of this form, it's like a squared, and there's like 2 times b, and here we have the b squared. So we can just write it then as a quadratic. And now essentially we have the form that we wanted, like that we know what's the integral of, because this essentially, so we can consider that this is the mu term of a Gaussian. This is the inverse of the quadratic, and this is again the mu term. Right? So now we can just like plug in the formula that we obtained for the PDF of a Gaussian, and with like some algebraic manipulations, we obtain that this is the marginal of b of x. So what this will mean is this mu x, it's the mean, and this term over here is the inverse of the covariance. So essentially we just have that the Gaussian variable x follows a Gaussian distribution with mu x and covariance matrix, which is sigma xx, by plugging the previous relationship that we found out between the precision matrix and the covariant matrix. So we have done all these manipulations because we didn't know beforehand what will be the form of the marginal of x. But notice that if we had known that the p of x will have inner Gaussian, we could just find out the mu and sigma. So that will make our lives way easier, because we know that the Gaussian variable is just parameterized by the parameter mu and the parameter sigma. This is like the mean and the covariance. So we could just like have found out the mean and the covariance of the variable x in order to find this distribution. But we assumed beforehand that we didn't know what was the form of p of x. So just a quick recap: if we have a joint distribution that follows this this partition variable with parameters like mu x, mu y, and all the covariance terms, marginalizing is pretty straightforward. It's just get the mu of the parameter x, and then the covariance of the parameter x also, and the same if you do it with respect to y. So you will have to work. It will be good for you to work through all the details how to essentially do the computation of squared trig. What I've essentially hinted in the proof before, but I just like sort of specify for this scalar case. But you should be able to work it out yourself and find out that this integral over here leads to the following result. So the other operations that we will need in order to fully formulate the Kalman filter is conditioning. So essentially we have the joint distribution P of x and y. If we know that the value of y is equals to this y0, what is the value of what's the probability distribution of x condition of y equals to this y0? Again, we'll work more or less through this daunting math, and it's using the exact same tricks. So here what we're saying is the probability of x given y equals to y0 is proportional, and that means that it doesn't depend on x to the joint distribution of x and evaluating y to y0. So just expanding again this expression, this quadratic expression, we find that it appears these three terms, one that just depends on x, this depends on x and y0, and this just depends on y0. Since we're just like finding like proportionals and this term doesn't depend on x, we can just completely drop it off and just say like, oh, all of this is again proportional to just the terms that depend on x and the parts that depend on x and this y0. And again, we can do the same. We see that this is like similar to a quadratic, but not yet a quadratic. So we will massage this expression by using this computation of square trig again. And the tricks are very similar here. We're just multiplying by 1 and just doing gamma xx times gamma minus 1xx, and just adding and subtracting the b squared term in the computation of square trig. So this term again, just the b squared term doesn't depend on x, so we'll just like move it away and say it's proportional. And now the other terms over here, just like they form a quadratic. So essentially you end up finding out that the condition of x with y equals to y0, it essentially gives this quadratic term. And this is again the Gaussian distribution, right? And now what we have instead is that the mean is given, the mu term is given by this that the mu will represent this term right here, and here it's missing actually a parenthesis, and then the inverse of the covariance will be given by the precision matrix, and then here we also have the mean again. So here's what we're saying, that x condition on y equals y0 follows a Gaussian distribution that has this mean, and it has covariance equals to the inverse of the precision matrix. So now we can just write it all in terms of covariances. It's a precision matrix, and this is the resulting Gaussian variable. So we see that the way that the mean moves is that we have this sort of like error term, or like deviation term, that like how far is this y0 with respect to the mean, and this is like the correlation between x and y. And essentially we also see that when you condition on y being equals to y0, you reduce uncertainty or the variance of the system, because here we're essentially from this covariance x, we're just subtracting this term that is positive. So this is just a recap of the formulas that we just found out, in case you want to access it later easier. So now we'll delve into the main part of this lecture. There's the Kalman filter. So you can consider a Kalman filter as a special case of the Bayes rule, but when the dynamics are linear and the measurements are also linear, and then if you start with a Gaussian variable and all the noise that you have in the system, it's also Gaussian, then what you end up having is like all the variables involved are also Gaussians, and then we can obtain algorithms that are like much more efficiently filter and recover this state. Because the underlying assumption is that we assume that we know the first state, so this like initial distribution, and then we have access to the measurements, but we don't have access to the underlying state. We don't have the xt, and given the measurements, we want to be able to recover what's the state of the system. And this is a pretty common case in robotics, where you directly don't have access to the state of the system, but you just have access to the sensors that you have incorporated into your robotic system. So also what this graph is saying is that the variable xt plus 1 just depends on xt and ut. So there is no further dependency. So if you know xt and ut, you are able to recover the distribution of xt plus 1. And then these zt's just depends on the underlying state. There is no other dependency. So there are 3 updates in this Kalman filter, and the first it's the time update. So the time update is just obtaining the prior that you know of xt plus 1 given xt. So here we don't yet assume that we have observed the measurements of the sensor. We just know that given xt and our dynamics model, what is the xt plus 1 that I predict. So here we assume that we know the probability of xt given the previous measurements and actions, and now we want to know what will be the distribution of xt plus 1. So we can just write this down as marginalizing the join of xt plus 1 and xt. And essentially this join, we can now apply the Bayes rule, and we could write it down as the probability of xt plus 1 given xt and all the measurements and all the actions times the probability of xt given, again, all the measurements and all the actions that we have here. So if we saw before in the graph, xt plus 1 just depends on xt and ut. So we can actually just throw away all the measurements in this term. And the other component over here is like the probability of xt given zt, given z of all the measurements, and u. This is what we assume that we know at this current time step. So you have like this sort of like inductive assumption. So we want to be able to find this joint distribution. And in order to find the joint distribution, we just need to find out this term over here, because we already know we assume that we know what's this probability of xt given the measurements and the actions. So we can expand out this term because we have the relationship between xt and xt plus 1 is linear. So essentially, if we go back to the first slide, now given xt, the only randomness in xt plus 1 is just the noise that we incorporated. So what this is saying that given xt, the random variable that xt plus 1 follows, it's a Gaussian variable centered in at times xt plus bt times ut, and then it has a, since there is no randomness here, the only variance in this variable is the one given by the Gaussian variable, this noise epsilon t. So essentially we have a Gaussian variable that is centered in this prediction of the dynamics and has the noise qt. So, and this is what we're saying here. We have this Gaussian variable that is like have mu, the one predicted by the dynamics, and the covariance is qt. And then the other term over here is just the one that we assume that it's known. It's just a Gaussian variable that has mean mu t given all the past and sigma t given all the past again. So in order to find this joint distribution, we can approach it two ways. One is like mold it as we had it before and just do all the tricks of computation of quadratics. Or the other way of finding it, it's by seeing that this is an exponential of quadratic terms, and hence, like, if you have an exponential of quadratic terms, this is a Gaussian distribution. So now we can just find the Gaussian distribution by finding its mean and covariance matrices, and this is essentially how you should proceed always, that you know that there is a Gaussian distribution, because it's much more convenient. Because now, in order to find the PDF of this joint, we just need to do the expectation of these variables and also find the covariance of these variables. So herein, a lot of daunting math, but it's pretty straightforward, and you should be able to work through it without looking at this slide. So essentially, we have that the joint distribution follows Gaussian distribution, because we saw that this is the exponential of a quadratic, and then we'll just define these parameters: mu t given the past from 0 to t, and then mu t plus 1 given the past from 0 to t. So here's where I said that we haven't conditioned on the current measurement. Once we condition the current measurement, we'll see that this condition will be from 0 to t plus 1. And the same for these covariances terms. So yeah, this is our assumption that mu t from 0 to t and sigma t from 0 to t, it's assumed to be known. So we know the underlying distribution of xt. And in order to find this, so you can work through all of this, but in order to find like this mu t plus 1 given the past, essentially what I explained before, you just plug the formula of the dynamics, and then you just take the expectation, and since everything is linear, you just have you end up having that the expected that the mean of the xt plus 1, it's just the dynamics evaluated on the mean of the previous time step. And yeah, you can work through all the covariances, but essentially just plugging the formula of the dynamics. And since everything is linear, you have that a lot of the terms of the noise just cancels out, and what you end up having is that the covariance is just a times the covariance of xt times a transpose, and then the extra noise, the extra uncertainty given by the noise. So this is the recap of the time update. We assume that we know the underlying distribution of the xt given all the previous measurements. And we have the formulas and dynamics. So we actually assume that we have the underlying dynamics, and we sort of like know how the noise is behave. So with these assumptions, then we find that the joint distribution of xt plus 1 and xt follows a Gaussian distribution with this mean and covariance. And now we can directly apply the formulas that we saw for the marginalization to obtain just the distribution of xt plus 1 given all the past. So this is the formulas that we saw in the multivariate Gaussian case. So this is true for any Gaussian variables that they're related with that they have a linear dependency. So if a Gaussian variable v follows a certain Gaussian distribution, and then we have that another Gaussian variable w is related linearly with this Gaussian variable v plus some extra noise that it's independent of v, then all that we have formulated here and developed just applies straightforwardly. So the other step, it's once you see the observation, so you have a system and you apply some action and you get to a new state, and then your sensors just apply just like send you the observation, and now given this observation you know more things about the underlying system. So you want to know what's the underlying system condition on this new observation. So now we assume we have the prior that we have obtained in the previous slides. So we know that we assume that we know xt plus 1 given the past, but we have already not seen the measurement. And then we assume that the way that the underlying state and their measurement relate is through this linear equation. So we have this ct that multiplies the ct plus 1 that multiplies the xt plus 1 plus some constant term, and then we have a noise that it's independent of all the previous random variables. So then we can just find again that the joint will be an exponential of a quadratic, and hence you can just find the parameters mu and sigma because you know it's a Gaussian variable, and just working through the math at the same way that we found the joint for the xt and xt plus 1. Now we can do the exact same steps to find the joint of xt plus 1 and zt plus 1. And once we find the joint distribution, what we can do is just condition on zt plus 1 equals to the measurement that we have seen here, lowercase zt plus 1. And we can just apply the equations that we obtain in the multivariate Gaussian case for the conditioning, and we can just apply those straightforwardly to obtain the Gaussian distribution that xt plus 1 given the previous measurements and actions, the distribution that this random variable follows. So with these two updates, we know the entire algorithm of the Kalman filter. So essentially how the system develops is that you start with some initial state that follows a predefined Gaussian distribution, and then at each step you alternate between predicting how your system will behave without actually knowing the measurement, and then incorporating the measurement into your beliefs to have like a more accurate state of your system. So people how usually write the Kalman update is by the means of this Kalman gain. That is essentially how much you have to rectify your system. So see that in the measurement update, the mean is given by the previous mean, and then you have this this error term that is given, like this is the actual measurement, this CT plus 1 is the measurement that you see, and this is how much it deviates from the mean. And then you just incorporate this into the next mean by the Kalman gain, or also known as innovation, that essentially determines how much your prediction has to change given the error that you have seen. And finally, this Kalman gain is also incorporated into it. Also appears in the expression of the covariance that essentially says how much you reduce your uncertainty by seeing this measurement. So this Kalman filter is like very much used nowadays because it's very efficient, and it gives you the optimal results. So essentially all the operations that we see, it just involves matrix multiplications. So this can be implemented like very efficiently, and we have the extra benefit that this is the optimal thing that you can do for Gaussian systems that are linear. So in the previous part, we saw like how to estimate the state of a system when all the transitions and all the measurements follow a linear function. But most of the real robotics problems involve like nonlinear dynamics. So essentially your function that maps from state and action to next state is nonlinear, and also the function that maps from state to measurement, it's non-linear as well. So, but we have the assumption that the function is deterministic, and you have to choose some extra noise on top of this function, and moreover that the noise is Gaussian. So in the linear setting, essentially what we have is that this function ft, the dynamics, has just the form of a linear function at times x plus bt times the action, and the function that computes the measurement in the linear setting is just a linear function of the state. So hc is essentially ct times x plus this dt. How like does like these linear nonlinear functions affect the probability distribution? So in the case that we have a linear function, this function y equals ax plus b, and we pass through it Gaussian distribution, what we end up having is another Gaussian distribution. The only thing is like this Gaussian distribution has a mean that it's different and a standard deviation that is different. So essentially is shifting and scaling the original Gaussian distribution. However, when we have nonlinear functions, the behavior is completely different. So for instance, here we have this function g of h, and we pass through it again a Gaussian function. However, in this case, the probability distribution, there's the gray part of this plot. It's non-Gaussian. It's not like even unimodal. Here we see that there's these two modes that appear. So the probability distribution that you pass through these two nonlinear functions can be arbitrarily. So it's very hard to determine and to compute the underlying distribution that appears when you pass Gaussians through nonlinear functions. Here, the blue curve, it's the Gaussian that most closely matches the distribution P of y, the gray one. So in order to find this Gaussian, essentially this Gaussian is to minimizing some distance from a Gaussian with parameters mu and sigma and the distribution P of y. And in this case, the distance that we use is the KL divergence. And so this is the closest Gaussian in terms of the KL divergence is the blue curve that we saw here. But in order to compute, so we know that the Gaussian is just parameterized by a mean and a standard deviation. So what we can do in order to find this Gaussian is to just compute the mean and STD of P of y and just assign those to a Gaussian. And this is the way that we can find also this Gaussian distribution of P of y. However, in order to compute the mean and standard deviation, we need to know the underlying distribution. So we have already done all the work of finding P of y, and that's the hard part. That's the part that's usually not tractable, is how to compute P of y. Hence, like, we don't know how to obtain analytically the Gaussian distribution of P of y. So instead, what the extended Kalman filter does, it's linearize the function g of x around the mean of the Gaussian. So essentially, we just take the first order Taylor approximation of the function, and the way that we compute the Gaussian is just through passing the Gaussian through the linear function that we just obtained. And we see that, like, the Gaussian that we obtain is not exactly the one that you will obtain by, like, minimizing the KL divergence, but in some cases it's close enough. So here we see a case where this, like, linearization fails, and this is essentially when you have high variance. The problem, like, when you have high variance is that you have a lot of points that are outside the realm where this function, with this approximation, this first order approximation of the function is valid. So in those cases, in the case that we have, like, high variance, we will end up with a Gaussian distribution that it's pretty different from the one that you will obtain if you were to fit the Gaussian to the true or underlying distribution. However, like, the benefit of this is, like, we very rarely work in those cases where we have high variance, because if we have high uncertainty of what's our state, that's actually not even good enough, even if you had the true distribution. Because if you cannot, like, accurately measure the state, you probably won't be able to do any control on top of it. However, in the case that we have little variance, then all the mass is centered around the mean. So all the mass is centered through points that are like sort of valid for the Taylor approximation. So in these cases, we see that the red curve and the blue one almost match, are almost identical. So in the case that we have low variance, then this AKF linearization, it's valid. So the way that compute the first order approximation, usually just evaluate the current function around the mean, and you compute the derivative of the function around the mean. There is, like, very often the case that the analytic derivative is not available, and people in such cases just use finite differences. So you can obtain this linearization by just doing finite difference. And then once you have the linear dynamics and the linearization for the measurement function, then you apply the exact same algorithm that we have obtained in the Kalman filter, but you just change the A, B, C, and D matrices to be just the linear terms that you have obtained in your linearization. So it's pretty easy and straightforward once you have the Kalman filter to just extend it to the nonlinear setup. So this algorithm is still very efficient. It's in the same order that the Kalman filter update. And it just depends how computationally expensive obtaining this derivative is. But it's the case that you have analytical derivative that is like really it's the same. It's really straightforward, and it's the exact same cost. The only problem is that it's not optimal anymore because we have like adding this extra assumption within this extra approximation on the nonlinear functions. Then what ends up happening is like one is not optimal, and two that it can diverge if this nonlinearity is high, especially when you have a lot of like multimodality. However, in practice works really well, and people use it a lot, and like there are like further extensions that are like more efficient and better, but in practice it works really well, and all of work has been done on top of these standard Kalman filters. Now we're going to explain the unscented Kalman filter, that it's another way of doing Kalman filtering when you have nonlinear dynamics. So because like essentially what the extended Kalman filter does is just linearizing the dynamics, doing the approximation of the dynamics, and then use all the machinery of the Kalman filter to compute the estimate of your state. What the UKF does instead is doing the approximation in the Gaussian of P of y, so the Gaussian distribution after the nonlinearity. And we do this approximation by sampling a specific set of points. So in that sense, the approximation that is carried out instead of being in the nonlinearity, it just happens in the distribution level. Here, this plot shows us the difference between doing UKF and EKF. So in the extended Kalman filter case, what we do is just pass this Gaussian to the Taylor approximation. So we'll have like this line over here, the Taylor approximation around the mean of the nonlinear function, and then this is the resulting, and then you use the resulting Gaussian for the Kalman filter. Instead, in the UKF case, what we do is sample a set of points. So here in this case, we'll sample the mean, and then 2 points that are certain distance away of the mean, and pass these 3 points, evaluating like analytically the nonlinearity, and then feeding a Gaussian distribution on the image of these 3 points. And we see that doing this procedure results to a more accurate Gaussian distribution than if we were to do the extended Kalman filtering. So here we see the case of when we have higher variance, and we saw that the EKF leads to a pretty poor approximation of the real Gaussian. Instead, if we use the sigma point estimate that the UKF gives us, it's a much closer approximation. So we see that the blue and the red curve are much more closer than the blue and red curve in the extended Kalman filter. And in the case that we have lower variances, then we see that both methods lead to fairly the same results. And you can actually prove, in the case of doing finite difference, that there's an equivalence between UKF and AKF, because you can consider if these sigma points are pretty close by, you can consider this as just doing finite differences. So there's like this analogy between the sigma point estimate and the extended Kalman filter. So essentially how the sigma point estimate works is that you have this set of points, that one will be the mean, and then the other points that are certain standard deviation apart from the mean, and then you pass these points through the nonlinearity, and this results in a set of points that are the image of this nonlinearity. And then what you do is just feeding a Gaussian distribution into these points over here. And why the UKF works better than just doing extended Kalman filtering. And the reason is that when we do extended Kalman filtering, what we're doing essentially is just removing all these terms on the tail, all the higher order terms of f, and we just keep on the function, the value of the function of the mean and the Jacobian. However, by doing the UKF method, what we do, we keep all the terms in the of the nonlinear function, because essentially we're evaluating exactly the function at the sigma points. But what we do is just approximating the n distribution, and that allows us to use all the moments of the nonlinear function and just trade off and just use the true moments for the Gaussian distribution that we want to evaluate, essentially because we need the mean and the covariance matrix. So the UKF essentially uses the minimal set of points in order to compute the mean and the covariance of the Gaussian function, the Gaussian of p of y, and the minimal set of points that the Unscented transform uses are the mean, and then all these points are like n plus k distance away from the covariance. So we see that these terms are this is the ith column. So essentially it just uses the axis of the covariance of the covariance and just scales it by this a square root of n plus k. And usually people use n plus k equals 3, but these k terms, this n plus k term, allows us you to fine tune the resulting distribution to be more accurate. So, and here, what it means here we're essentially taking the square root of a matrix, and this essentially what it means is any matrix such that if you multiply it to its transpose leads to the covariance. So this P of XX, it's a sigma that we've been seeing, is the covariance matrix of the random variable x. So once we do the Unscented transform and we obtain the sigma and the mean, we can simply use the Kalman filter update, because now we have a Gaussian distribution. So then you can almost apply straightforwardly the Kalman filter approach that we saw in the past. And then to compute the covariance between the points x and the z, there are the measurements. You just use these sigma points that comes from the Unscented transform, and you can just compute the covariance between the points before and after the nonlinear transformation. So here, just for reference, the entire algorithm that leads to the Unscented Kalman filter, and you should take a look at it and make sure to understand each of the steps. But it's essentially the steps that I just go through. So as a summary, this is more efficient than the AKF, and in practice it just runs faster, and it leads to better results. And the further benefit is that in most cases exact derivatives are not available, and people obtain them by just doing finite difference. And this is computationally pretty slow, especially when you go to higher dimensional systems. So in general, like this UKF leads to a better performance, and it's faster than usually than doing EKF. However, the same as extended Kalman filter, this approach is still not optimal. So this is the lecture of today, and in the next lectures we'll see how to estimate the transition dynamics and the measurement functions, because essentially we have just assumed in the entire lecture that we know the underlying dynamics of the systems and we know the measurement, but this is actually not always the case. So we will develop algorithms in order to estimate these variables as well. And the other thing that we'll see is how to do smoothing. Essentially, if we have seen more steps in the past, can we refine our predictions of what were if we have seen more steps into the future, can we refine our predictions of what were the underlying state as at a past time step? So all of this we'll see it on next Tuesday.